The storm had already gone. That's the part nobody could make sense of afterward. It came through Chicago on the morning of June 26, 1954, a Saturday, moving fast and low out of Wisconsin. At the Wilson Avenue Crib, a squat intake structure sitting about 2.5 miles offshore in Lake Michigan, the instruments caught the whole passage. Wind went from nothing to roughly 56 miles an hour inside a single minute. The barometer jumped about 3 millibars in 4 minutes, which sounds like nothing at all, and we're going to come back to why it isn't. Then the squall line kept traveling southeast, out over open water, and the wind at the crib fell away to 0 over the next half hour. By 8 in the morning, it was finished. Blue sky over the lakefront, flat water. The kind of morning where the city exhales, and everybody who canceled their plans an hour earlier decides to go ahead after all. People went back to the piers. Going back out there was the single most reasonable decision anyone made that day. A storm passed. The storm ended. The lake looked like a pane of glass. Around 50 people walked back out onto the breakwater at Montrose Harbor, on the north side of the city, most of them fishing. An Illinois conservation officer named Herbert Reederer was out there writing a ticket to a man fishing without a license. Down at North Avenue Beach, the lifeguard captain on duty was a 24-year-old named Joseph Pecoraro. Ordinary Saturday. At roughly 9:30 in the morning, more than 2 hours after the storm had cleared the shoreline, the water came up. It didn't break the way surf breaks. Witnesses described it as a rise, a fast one, water climbing over the concrete and running inland with force behind it. One man who lived through it said it felt as though somebody had put a giant hand into the lake and pushed it up into his face. Along the Illinois shore, the rise ran maybe 2 to 4 feet in most places. At the North Avenue groin, it was reported at closer to 10. Beaches flooded as far as 50 yards inland. The breakwater at Montrose, which stands a few feet above ordinary lake level and is dry in any normal weather, went under. 8 people did not come back. 7 of them were swept from the piers at Montrose Harbor, 1 from the beach at North Avenue. 3 were recovered that same morning. The rest took over a week, partly because the lake would not settle down. The Chicago Daily News reported that recovery work was fought by strong currents and clouded water for something like 34 hours afterward on a lake that, from the shore, looked calm. On July 8th, a coroner's jury delivered a verdict. The deaths, it found, were caused by a seiche brought on by atmospheric conditions, otherwise an act of God. Read that sentence again and notice what it's doing. It names a mechanism, a seiche, and then it hedges the mechanism with a phrase that means, "We have no further explanation." The jury wasn't being lazy there. That was simply the state of knowledge. Seiche was the word available in 1954 for water in a lake doing something water in a lake shouldn't do, and the word had been in use for a century, and it described a real thing. It just didn't describe this. A seiche is a lake sloshing. It's slow. On Lake Erie, the classic case, the whole basin tips and rebounds on a rhythm of about 14 hours. 14 hours? Not 14 minutes. And a seiche needs a reason to be tipped in the first place, which means hours of hard wind pushing water toward one end of a lake before the water can come sliding back. That morning, the wind had lasted half an hour and then quit. The lake surface at Chicago was flat before the wave and flat again after it. There was no tilt to release. So something crossed Lake Michigan that morning that behaved like a tsunami. It arrived as a rapid rise. It hit a shoreline with no visible warning. It came from a direction the storm had already left. It killed people standing on a structure they'd stood on 1,000 times before. In weather so mild that going out there was the sensible thing to do. And there was no earthquake. There is essentially never an earthquake here. The Great Lakes sit in the middle of a continental plate, a long way from any subduction zone, and the seismicity of the region is the geological equivalent of background hum. Whatever lifted that water had nothing to do with the ground, which leaves the sky. Now, 3 months after those funerals, a paper appeared in the journal Science. 3 authors, all from Lamont Geological Observatory at Columbia: Morris Ewing, Frank Press, and William Don. Ewing and Press were serious names in seismology, people who spent their working lives listening to the planet ring. Their paper was short. It was titled, plainly, An Explanation of the Lake Michigan Wave of June 26, 1954. And what they proposed was that the atmosphere had done it. That the pressure jump riding along with that squall line had pushed a long wave across the lake, and that the wave had grown as it went, because the storm and the water happened to be traveling at almost exactly the same speed. That paper is the reason this subject exists as a field. It is also, in a couple of important places, wrong. And the corrections took 60 years and a supercomputer. One thing worth being clear about at the start: there are at least 3 different explanations that have been offered seriously by competent people for waves like the one that hit Chicago. One of them is the seiche, which the coroner reached for. One is storm surge, which is what a lot of these events get filed as after the fact. And one is the pressure-driven resonant wave that Ewing, Press, and Don proposed. They are not variations on a theme. They make different predictions. They leave different fingerprints on an instrument record, and they can be told apart if you have the instruments. The Great Lakes, as it turns out, mostly didn't. And still, mostly don't. What follows is an argument, not a tour. We're going to put the 3 explanations side by side, run each one against what the gauges actually recorded, and find out which pieces of each survive. 2 of them will lose, though not in the way you'd expect, and the one that wins will need serious repair before it works. Along the way, we'll end up somewhere I didn't anticipate when I started reading the case files, back in the 1880s and 1920s, looking at a column of drownings on the Great Lakes that were written down at the time as freak waves and tidal waves, filed and forgotten, and asking a harder question than whether those old accounts were true, asking whether we can now say what happened to those people, and being honest about where the answer is no. Start with the lake itself, because before any of the 3 explanations make sense, you have to understand what kind of physical object a Great Lake is, and why it is capable of carrying a wave that behaves like something out of the deep Pacific. Pull the map over and look at what you're actually dealing with. 5 lakes. And they are not small. Lake Superior alone holds enough water to cover the entire lower 48 states to a depth of about 5 feet. Lake Michigan runs roughly 307 miles from the top of the basin down to the Indiana shore, which is the distance from Boston to Baltimore, and it's the only one of the 5 oriented north to south, which is going to matter enormously later. Lake Erie is the runt on depth and the giant on trouble. It averages about 62 feet deep, which for a body of water 240 miles long is closer to a puddle than a sea in proportional terms. Lake Superior averages 483 feet. Lake Michigan averages 279, with a deep trough in the middle, running past 900. Those depth numbers are not trivia. In this story, depth is the control variable. Depth is the thing that decides whether a lake can be hurt. Here's why. In deep water, waves are slow and they're picky. A wave in the open Pacific with a 15-second period travels at a speed that depends on its own wavelength and doesn't care much what the bottom is doing thousands of feet below. But once a wave gets long enough, long compared to the water it's sitting in, the rules change. It becomes what physicists call a shallow water wave, or a long wave, and its speed stops depending on the wave and starts depending only on the depth. The formula is about as simple as physics gets. The speed is the square root of gravity times the depth. That's it. 2 numbers, 1 square root. Run it. In 66 feet of water, a long wave travels about 31 miles an hour. In 200 feet, about 54 miles an hour. In 330 feet, about 70 miles an hour. Lake Erie's central basin, at around 60 feet, carries long waves at roughly 30 miles an hour. Lake Michigan, on its average depth of 279 feet, carries them at about 65. Hold those two numbers, 30 and 65, because they're the whole engine of this story, and we're going to walk right into them. Now, the important part, notice what those speeds are. 30 miles an hour is the speed of a thunderstorm complex drifting across Ohio on a July afternoon. 65 miles an hour is the speed of a fast squall line, or of a derecho, that long-lived windstorm that comes off the plains and runs for hundreds of miles without weakening. Those speeds are utterly ordinary. Those are Tuesday. The Great Lakes, in other words, are shaped so that the water underneath moves at the same speed as the weather on top. That is a coincidence of geography with consequences. And it is not a coincidence the ocean shares. To get an ocean-long wave moving at 30 miles an hour, you need to be on a shallow shelf. Most of the ocean is 400 times deeper than Lake Erie. And long waves out there travel at 500 miles an hour, which no storm on Earth can keep up with. The lakes are exactly the wrong size. Big enough to build a wave, shallow enough to let a storm push it. And calling what happens here a tsunami is a technical statement rather than a colorful one. That needs nailing down before we go further, because the word has been so completely welded to the word earthquake in most people's heads that applying it to a freshwater lake in the American Midwest sounds like tabloid language. The classification is about period. It has never been about cause. The National Ocean Service defines the tsunami frequency band as waves with periods between 2 minutes and 2 hours. Period is the time from one crest to the next. Ordinary wind waves on a lake have periods of a few seconds. A seiche on Lake Erie has a period of about 14 hours. A tsunami sits in between, and the gap is enormous in both directions. A wave with a 10-minute period is a fundamentally different animal from a wave with a 6-second period. In the same way, a freight train is a different animal from a bicycle, even though both have wheels. It carries a colossal amount of water. It doesn't break offshore and dissipate. It arrives as a rise, keeps rising, and then, on the way out, keeps falling. A wave in the tsunami band generated by an earthquake is a seismic tsunami. A wave in the tsunami band generated by the atmosphere is a meteotsunami. Same band, same behavior at the shore, different power supply. The word has been in the scientific literature since the 1960s, and the phenomenon itself has local names in half a dozen coastal cultures that have been living with it for centuries. In the Balearic Islands, they call it a risaga. In Croatia, a siga. In Nagasaki Bay, a biki. In Sicily, marrobio. In Malta, milguba. Every one of those words predates the physics by generations, because people who fish for a living notice when the harbor empties out for no reason. The Great Lakes never got a folk name for it. Some places got a word and never got an explanation. The lakes got neither, and I think that's part of why the record here is such a mess. When a fisherman in Minorca said risaga, everyone within 50 miles knew exactly what he meant and roughly what it would do. When a fisherman in Grand Haven, Michigan said the water came up, there was no category to put it in, so it went into the newspaper as a freak wave or a tidal wave, and into the county record as a drowning, and nowhere else. NOAA's Great Lakes Environmental Research Laboratory says this outright in its own public material. For most of the historical record, these waves were misidentified as freak waves, tidal waves, or seiches. So here's the actual problem. There are 3 explanations on the table for a sudden, tsunami band rise of water on a Great Lakes shoreline. All 3 are physically real phenomena. All 3 happen on these lakes, routinely, and all 3 can produce a shoreline that's higher than it was 10 minutes ago. The first is the seiche, a basin-wide sloshing, driven by wind piling water toward one end and then letting go. The second is storm surge, or wind setup, the same wind piling the water up, but considered while it's still piled, before any rebound. On Lake Erie, this reaches magnitudes that sound made up. The third is the one Ewing, Press, and Don proposed, a long wave in the tsunami band, generated by the pressure jump and the wind burst traveling with a squall line, amplified because the storm and the wave happen to be moving at the same speed. An honest investigation doesn't start with the answer, so we're going to take them in order, give each one a serious hearing, and ask 3 questions about each. What does it explain well? Where does it fail? And, most importantly, what evidence would prove it wrong? Because an explanation you can't falsify amounts to a mood with vocabulary. Start with the seiche, because it has the strongest claim of the 3. It's real, it's enormous, it's been documented on these lakes since the 1800s, and for about 100 years, it was the only answer anyone had. The word comes from Lake Geneva. Fishermen on the Swiss shore used it for centuries to describe the way the lake would rise and fall at the quays on a slow, regular beat, with no wind to account for it. And in the 1870s, a Swiss naturalist named François-Alphonse Forel finally worked out what they were watching. The lake was rocking. The entire body of water, end to end, tipping down at one shore and up at the other and back again, like coffee in a mug that somebody has just set down hard. That's a seiche. It's a standing wave. The distinction matters, and it's going to do a lot of work for us, so let's be concrete about it. A traveling wave moves. You can watch a crest leave one place and arrive at another. A standing wave doesn't move, it pulses. Picture a jump rope held at both ends and shaken. The rope goes up and down violently in the middle and barely moves at all at the ends. The high spot doesn't travel down the rope. It sits there and oscillates. That's what a basin does when it seiches. There are fixed places, called nodes, where the water level barely changes at all while the shorelines at either end go up and down by feet. The period of that oscillation is set by the shape of the container, and nothing else. Longer basin, slower rhythm, deeper basin, faster rhythm. There's a formula from the 1820s, the Marion formula, that gets you close. Twice the length divided by the long wave speed, which we already know is the square root of gravity times depth. Run Lake Erie through it, and you get somewhere near 15 or 16 hours. The number people actually measure is about 14 hours and change, and the gap between calculation and measurement is itself informative. Because Erie isn't a bathtub. It's 3 basins of different depths welded together, and the sloshing waits itself toward the deeper eastern end. Lake Superior comes out around 8 hours, Lake Michigan around 9. Every one of those is a whole working day. That's the first thing to fix in your head. A seiche is among the slowest things a lake does, but slow does not mean small, and Lake Erie is the proof. On December 30th, 2025, a winter storm came through with gusts running 60 to 80 miles an hour along Erie's long axis. Buffalo, at the eastern end, went up about 8 feet. Toledo, at the western end, went down about 6. That's a 14-foot difference between 2 ends of the same lake, at the same moment, in a body of water whose average depth is only 62 feet. Roughly a quarter of the lake's depth tilted. In November of 2003, Buffalo saw a rise of about 7 feet, with 10 to 15 feet of wind waves stacked on top of the raised water, which is where the eye-catching 22-foot figure in some accounts comes from. 3 different processes in one headline number, and untangling them is a chronic problem in this whole subject. Go further back and it gets worse. On October 18th, 1844, a storm drove Erie's water into the eastern end with such force that the surge came over a 14-foot seawall at Buffalo. The recorded rise was around 22 feet. 78 people died. That remains one of the deadliest water events in the history of the lakes, and there is nothing mysterious about it. It was wind. Enormous, sustained, perfectly aligned wind. So why Erie? Over and over. 2 reasons, and they compound. The first is that wind setup, the piling of water toward the downwind end, scales inversely with depth. The shallower the water, the more it piles. The physics is intuitive if you think of it as the wind dragging on the surface and the water column having to push back. A deep column has a lot of mass to resist with. A shallow one has almost none. Erie's 62 feet against Superior's 483 means Erie responds something like 8 times more strongly to the same wind. Superior can take a gale and barely notice at the shoreline. Erie takes the same gale and empties Toledo Harbor. The second is orientation. Erie runs west-southwest to east-northeast, which is almost exactly the axis storm winds prefer in that part of the country. The lake is aimed at the weather. And setup scales with the square of wind speed, so doubling the wind quadruples the pile. 40 miles an hour gives you a couple of feet across the lake. 60 gives you 11. 67 gives you 18. Now, does that explain the Chicago wave? Give the Seiche the fairest hearing you can, because it deserves it. It explains a huge amount. It explains Buffalo. It explains Toledo. It explains why boats end up sitting on mud in a harbor that was fine an hour ago. It explains long stretches of the historical damage record on all 5 lakes, and it very likely explains a fraction of the drownings in that record too. Because a lake that drops 6 feet and then comes back has moved a spectacular amount of water past whatever was standing in the way. And it fails on the 1954 event, on 5 separate grounds, any one of which would be enough. Grounds 1, period. Erie's fundamental rhythm is about 14 hours. Its harmonics, the faster modes the basin can also ring at, divide that down. Second mode, 7 hours. Third, about 4 3/4. Fourth, 3 1/2. Fifth, about 2 hours and 50 minutes. Even the 5th harmonic sits outside the tsunami band, which tops out at 2 hours. To get a wave with a 10-minute period, you would need a basin to ring at a mode so high the arithmetic stops being physical. A Seiche cannot deliver a crest that arrives and departs inside a quarter of an hour. It isn't a matter of degree. The container won't do it. Grounds 2, the precursor. A Seiche is a release. Something has to load it first, and the loading is hours of sustained wind along the long axis. That leaves an unmissable trace. Before the water comes back, the wind blew hard, and it blew for a long time, and it blew from a consistent direction. Chicago on that Saturday had 30 minutes of wind, and then nothing. There was no tilt in the lake to release, because nothing had spent the morning tilting it. Grounds 3, geometry. A Seiche is standing. Its high point sits at the ends of the basin and doesn't travel. But that morning, the disturbance demonstrably moved. It reached Milwaukee at one time, Michigan City at another, Waukegan at another, Gary at another, Ludington last of all, and the arrival times spread out across the lake in a pattern that traces a path. Something was going somewhere. Standing waves don't. Grounds 4, rate. GLERL, NOAA's Great Lakes Lab, describes the fast events as rapid changes in water level over a few minutes to an hour. A Seiche moves water over hours. It's the difference between a tide and a slammed door. Grounds 5, shape. A Seiche is by definition oscillatory and symmetric. It goes up, it goes down, it goes up, and it does that for a day or more with a rhythm you can set a watch by. The signature at Chicago was a single dominant surge followed by a drawdown, with the aftermath being messier and less regular than a Seiche has any business being. That's what falsification looks like, by the way. A test with a predicted outcome rather than an argument you can win by talking. If the Seiche explanation is right, then 2 things must be true in the record. The oscillation period must exceed roughly 3 hours, and the hours before the event must contain sustained strong wind along the lake's long axis. Go look. If either is missing, the Seiche is out. For June 26, 1954, both were missing. which is not a small thing to have established because it means that for about 70 years, from the 1880s to the 1950s, the standard explanation for tsunami-band waves on the Great Lakes was an explanation that could not physically produce them. Every event that got labeled a SH and closed in that period is a file that was never actually opened. But before we hand the case to the atmosphere, there's a second explanation to dispose of. And this one is sneakier than the SH because it doesn't fail on physics. It fails on bookkeeping. Storm surge on the Great Lakes is real, it's routine, and it is the most underappreciated hazard on these shorelines. Nobody in this story is arguing otherwise. The problem with it is different. Storm surge is not a bad explanation for what happened at Chicago. It's a bad explanation that keeps getting applied to events after they're over by people working from records that cannot tell the difference. And the result is a historical archive so scrambled that even the researchers who assembled it disagree with each other about basic facts. Let me show you exactly how that happens, because once you see the failure mode, you can't unsee it. And it changes how you read every historical account of water doing something strange on these lakes. Start with the most quoted number in this entire subject. The Chicago wave of 1954 is universally described as a 10-foot wave, about 3 meters. It's in the NOAA fact sheets, it's in the papers, it's in every retrospective. The instrument that recorded that event measured roughly 3 feet. Both numbers are correct. They're measuring different things. The 10-foot figure is a shoreline observation, run up. What the water did when it climbed a beach or slammed into a groin and piled up against concrete. The 3-foot figure is what a water level gauge recorded in the lake. A wave arriving at a shoreline does not stay the height it was offshore. It shoals, it steepens, it runs up a slope, it gets funneled into a harbor mouth and amplified there. So the gauge and the eyewitness are both telling the truth. And if you don't know which one you're holding, you are off by a factor of 3 before you begin. That single confusion is responsible for most of the bad numbers in circulation about the Great Lakes. And it works in both directions, which is the part people miss. Sometimes the shoreline number is inflated by panic and memory. Sometimes the gauge number is deflated by the instrument itself, and that turns out to be systematic. And we'll get to how badly. Now stack the second problem on top, wind waves. That November 2003 event at Buffalo gets reported as 22 feet. 7 feet of that is the water surface being raised by the wind. The other 10 to 15 is ordinary wind waves riding on top of the raised surface. 2 completely different processes, one on a timescale of hours and one on a timescale of seconds, summed into a single figure and printed. If you're a historian in 50 years reading that clipping, you have no way to take it apart. Third problem, things add. The National Tsunami Hazard Mitigation Program says this explicitly in its modeling guidance. A meteotsunami can combine with other phenomena, storm surge among them, producing further enhancement of the local water level. So a gauge record can contain a slow surge and a fast wave at the same time, superimposed. And what you read off the paper is one curve with 2 causes braided together. Whichever cause you were expecting to find is the one you'll see. Here's what those 3 problems do to the historical record when you put them together. On May 31, 1942, something happened on the Lake Erie shore near Cleveland. Boats capsized. The Toledo Blade ran a headline about a freak tidal wave sweeping the Lake Erie shoreline with 8 believed drowned. It's a documented incident with documented deaths. 2 peer-reviewed papers by overlapping groups of the same researchers list that event. One of them puts it at about 15 feet with 7 fishermen drowned. The other puts it at about 1.5 feet with no deaths recorded. Same event, same field, same decade of publication. A tenfold disagreement on height and a total disagreement on whether anybody died. It matters exactly what that does and doesn't mean, because it would be easy to turn it into a cheap shot at the researchers. And it isn't one. Those compilations are exactly what they say they are. Tables assembled from whatever survived, newspapers included, to establish that a category of event exists, and roughly how often. They were never presented as a vetted casualty database. And the same table contains a couple of citation slips that give the game away about how it was built. One entry, a 1960 event at Waukegan, Illinois, is credited to a paper published in 1956, which is a neat trick. Another, a 1912 event at Kenosha, Wisconsin, is credited to a source dated 1905. Those errors are small and they're honest, and they are also a warning label. The pre-instrumental record of Great Lakes water events is a pile, and calling it a dataset flatters it. So the storm surge explanation fails, but notice where. It doesn't fail as physics. Surge is perfectly real, and it does everything it's advertised to do. It fails as a diagnosis, because it's the explanation that gets reached for when the evidence is too coarse to support any explanation at all, and it's almost impossible to rule out from a newspaper account. Water came up, boats got wrecked, people drowned. Every one of those sentences is compatible with a 14-hour tilt of the basin and with a 12-minute wave, and if all you have is the sentence, you cannot choose. Which tells you exactly what evidence would settle it, and this is the piece that eventually cracked the whole field open. You need a continuous water level record with fine enough time resolution to see the shape of the oscillation. Then you do something that sounds like a technicality and is actually the entire discriminator. You high-pass filter it. A high-pass filter throws away everything slower than a chosen cutoff and keeps everything faster. The standard cutoff for this work is 6 hours. Filter a gauge record that way, and every slow process vanishes. Seasonal lake level, gone. The annual cycle, gone. Wind setup building over an afternoon, gone. The 14-hour seiche, gone, along with all its harmonics down to the fifth. What's left on the paper is only the fast stuff, and then you go looking, in what's left, for individual waves with a period under 2 hours and a height above about a foot. That's it. That's the test. It's not a judgment call. It's an arithmetic operation you can run on 100 years of tape. Anything that survives the filter is not a seiche and is not a surge, because neither of those can exist above the cutoff. Anything that survives the filter and that lines up with a barometric jump or a wind burst passing over the lake is something else entirely. When somebody finally ran that operation across the whole Great Lakes gauge network, the answer that came back was not what anyone was braced for. We'll get there, and the number is hard to believe the first time you see it. For now, the scoreboard. The seiche is out on the individual event, though it stays in as a major hazard in its own right. Storm surge is out as a diagnosis, though it stays in as the reason the old record is unusable. Both survive as real phenomena. Neither survives as the answer to what killed 8 people on a clear morning in Chicago, which leaves the third explanation standing alone. And now we have to find out whether it can carry the weight, because Ewing, Press, and Don proposed something that, on the face of it, sounds absurd, that a change in air pressure roughly equal to what you feel riding an elevator up 8 floors could kill people 2 hours later and 40 miles away. Air has weight. Everybody knows that in the abstract, and almost nobody carries it around as a physical intuition. So let's make it concrete. The column of atmosphere standing on your shoulders right now weighs about 14.5 pounds for every square inch of you. When a weather system moves in and the barometer falls, that column gets lighter, and the water underneath it, being a fluid that can't tell the difference between a hand and a sky, rises very slightly to compensate. The relationship is clean. 1 millibar of pressure change moves the water surface about 0.4 of an inch. So the squall line that crossed Lake Michigan on that Saturday morning, with its 3 millibar jump, was pressing the lake down by about 1.25 inches. 1.25 inches. That is the entire raw forcing. That's the whole account before anything clever happens. You could not detect it standing in the water. A boat wouldn't feel it. And the wave that came ashore at the North Avenue groin 2 hours later was reported at 10 feet. That's a factor of roughly 100. Somewhere between the pressure jump and the concrete, something multiplied the effect by 2 orders of magnitude, and if you can't name that something, you don't have an explanation, you have a coincidence. The name is resonance. And the version that matters here was worked out in 1929 by a British oceanographer named Joseph Proudman, which is why it carries his name. Proudman's insight is one of those things that seems obvious in retrospect and is deeply not. Take that pressure dimple, that 1.25 inches of depressed water, and move it across the lake. If you move it slowly, the water just responds locally. It sags under the low pressure, recovers behind it, and nothing accumulates. If you move it very fast, the water can't keep up at all. It barely responds, and again, nothing accumulates. But if you move it at exactly the speed the water's own long waves travel, the dimple and the wave stay locked together. Every second the disturbance spends over the lake, it is pushing on the same piece of water it pushed on a second ago. The forcing stops being a nudge and becomes a sustained shove, applied to a wave that's already moving at exactly the speed you're pushing it. Kids figure this out on swings before they can spell it. Push at random and nothing happens. Push in time and a small effort produces an enormous arc. The mathematics is unforgiving about how narrow the window is, and that's the part that surprised me. Write the storm's speed as a fraction of the wave's natural speed. If the storm is going half as fast as the wave, the amplification is about 1 1/3. Not much. At 70% of wave speed, about double. At 80%, under 3 times. At 90%, about 5 times. At 95%, about 10 times. Look at that progression. Nothing much happens until you're within roughly 10% of the match, and then it climbs a cliff, which is exactly why these events are rare, even though squall lines are ordinary. The lakes get hit by fast-moving convective storms constantly, all summer, every summer, and almost every one of them produces a shrug of an inch of water and nothing else. It is only when the speed lands inside that narrow slot that anything grows. And at the perfect match, the arithmetic changes character. The amplification stops being a fixed multiplier and becomes a function of distance. The longer the storm and the wave travel together, the bigger the wave gets, without limit, until the storm changes speed or the coast arrives. Fetch becomes the resource being spent. 100 miles of match travel builds something. 250 miles builds something dangerous, which is, again, exactly the size of a Great Lake. Not a coincidence anymore. A design specification the geography happens to meet. There's a nice, slightly absurd 19th century footnote to all this that I think about every time I read a Proudman resonance paper. In August of 1834, a Scottish engineer named John Scott Russell was standing beside the Union Canal near Edinburgh, watching a barge being towed by a pair of horses. The horses stopped abruptly. The boat stopped, and the mass of water the boat had been pushing along in front of it did not stop. Russell watched a smooth, rounded heap of water, a foot or so high, roll away up the canal, holding its shape, showing no sign of falling apart. He got on a horse and chased it. He followed that single hump of water for a mile or two at 8 or 9 miles an hour before it finally got away from him in the windings of the channel. He called it the wave of translation, and he spent years afterward trying to convince a skeptical scientific establishment that he'd seen anything at all, because the accepted theory of the day said such a thing could not persist. Russell's wave and a meteor tsunami aren't the same creature, and I'd rather not pretend they are. His was a solitary wave, a soliton, with its own particular mathematics. But the thing he stumbled onto, and the thing that made it possible for a man on a horse to keep pace with a wave, is the same physical fact underneath this entire story. Shallow water has a preferred speed. It's set by depth, and it's slow enough to chase. Match it, and the water will carry your disturbance for you, indefinitely instead of scattering it. A canal in Scotland is 8 or 9 miles an hour of preferred speed. Lake Erie is 30. Lake Michigan is 65. Storms come in all three flavors. Now run the 1954 numbers. Ewing, Press, and Don did something rather elegant to get their storm speed. They didn't have radar coverage of the lake. What they had was a ring of weather stations around the basin, each of which had recorded the moment the pressure jump arrived. From those arrival times, you can triangulate the front's speed and heading the same way you'd locate an earthquake from seismograph arrivals, which was, of course, exactly the trade Ewing and Press were trained in. Their answer? The squall line was moving at about 65 miles an hour, on a heading of 135 degrees, straight southeast from Chicago toward the Michigan shore. And the path it took ran for a long stretch over water between 245 and 300 feet deep. Long wave speed in that band, 60 to 67 miles an hour. 65 against 60 to 67. The storm and the lake were traveling together, in step, for something over 100 miles. There's a detail in the later modeling work that I like because it shows the mechanism has teeth, rather than being a story you can tell about anything. Lake Michigan is not uniformly deep. There's a trough down the middle running past 500 feet, and over that trough, the long wave speed climbs close to 90 miles an hour, well clear of the storm. The match breaks. And when researchers modeled the event decades later, that's precisely what the wave did. It grew across the resonant depth band, then stopped growing over the deep water, then resumed when the bottom shallowed again toward the Michigan shore. The lake has a resonant zone, and the wave only fattens inside it. You can watch the growth switch off and back on as the bottom changes underneath. That is not the behavior of a coincidence. So the third explanation has a mechanism, it has numbers that check out, and it has a fingerprint. It should be time to declare a winner. It isn't. Because when George Platzman sat down 4 years later and actually computed the thing, the pressure-only version of this explanation came out roughly half the size it needed to be. George Platzman was a meteorologist at the University of Chicago, and in 1958 he did something that, in retrospect, looks like the beginning of an era. He built a numerical model of Lake Michigan and made the storm cross it again. Understand what that meant in 1958. Numerical weather prediction was about a decade old and still faintly disreputable. Computers were room-sized, temperamental, and rented by the hour. Platzman chopped the southern basin of the lake into a grid with squares roughly 2.5 miles on a side, wrote down the equations governing shallow water, put a moving pressure disturbance on top of it, and integrated the whole thing forward in time step by step to see what the water would do. He was, in effect, trying to reproduce a death from first principles. And what he got was a wave. It was just half the size. Platzman's pressure-forced model, faithfully fed with the pressure jump that the Wilson Avenue crib had actually recorded, underpredicted the observed water heights by about a factor of 2. Not a rounding error and not a modeling wobble, half. That's a serious result, and it's serious in a specific direction. It doesn't say Ewing, Press, and Don were wrong about resonance. The model built a wave, in the right place at roughly the right time, by the mechanism they'd proposed. What it says is that pressure alone doesn't carry the energy budget. Something else was contributing, and until you find it, you're explaining half an event. Before we get to what was missing, Platzman did one more thing with that model. And I think it's the single most persuasive piece of evidence in the entire 1954 case file. He detuned it. He ran the storm across the lake again and again at different speeds, holding everything else constant, and measured how much energy got transferred into the water each time. If the resonance theory is right, that curve should have a sharp peak, and the peak should sit at the long wave speed of the lake. If the resonance theory is a story people tell, the curve should be flat or lumpy or peak somewhere random. The peak came out at about 65 miles an hour, which is where the actual storm was. The real event had landed almost exactly on the worst possible speed for Lake Michigan. Platzman had shown, without needing anyone to take his word for anything, that the lake has a preferred frequency, and the storm hit it. And then he did something in 1965 that deserves more attention than it gets. He turned the model into a lookup tool. Charts, essentially, where you enter a disturbance's speed and its heading and read off the maximum wave height it should produce and when it should arrive. Nomograms, they were called, and they are a forecasting product built in the mid-1960s for a hazard that did not have a name yet. The tools for adapting to this thing started existing 11 years after it killed 8 people. Whether anyone used them is a different question, and a bleaker one. Now, the missing half. It took until 2014 to settle, and it was settled by 2 researchers at the University of Wisconsin, Adam Bekla and Chin Wu, who went back to the 1954 events with a modern 3-dimensional hydrodynamic model on an unstructured mesh, meaning the grid could be coarse out in open water and tightened down to about 100 feet of resolution near the coast, where the shoreline shape matters. Roughly 110,000 elements, 10 layers in the vertical, a 25-second time step, the whole lake. They forced it 3 ways: pressure alone, wind alone. Both together. Pressure alone came up short, the same way Platzman's had. Wind alone came up short too. Both together reproduced what the gauges recorded. Their split by height contribution came out around 60% pressure and 40% wind stress. That is a real correction to the founding paper, and it matters what kind of correction it is. Ewing, Press, and Don didn't consider wind stress at all. Neither did Platzman in '58. The mechanism they proposed was a pressure wave, full stop, and that framing has propagated through popular accounts of meteor tsunamis for 70 years. You will still read, in perfectly respectable places, that a meteor tsunami is caused by a jump in air pressure. For a substantial fraction of Great Lakes events, that is not what mainly caused it. A later study by Alejandro Linares, working with Wu and Bechle, and with Eric Anderson at NOAA's Great Lakes Lab, went through the northern Lake Michigan events specifically and found that 44% of them were initiated primarily by wind stress, and that 63% had a considerable wind stress contribution. Wind, not pressure, doing the majority of the work in nearly half of them. Now, I want to be straight about what that does to the strength of this explanation, because it isn't purely good news for it. An explanation with one forcing term is easy to falsify. Measure the pressure jump, compute the response, compare. An explanation with 2 forcing terms, whose relative weights vary from event to event, has more room to fit whatever it's shown. That's a real epistemic cost, and it should make you slightly more suspicious of the theory, not less. What keeps it honest is that the resonance condition doesn't get any softer. Wind or pressure or both, the disturbance still has to travel at the long wave speed of the water beneath it, or nothing grows. That condition is a hard number. It comes from the bathymetry, and it can be checked against radar and surface observations for every single case. When researchers reconstructed a Lake Erie event decades later, they went into the Doppler radar data and measured the outflow speed directly. It came out at the resonance speed for that basin. When they did Warren Dunes, same test, same result. The theory keeps making a prediction that could embarrass it, and keeps not being embarrassed. There's one more result out of the 2014 reanalysis that I find quietly unsettling. They asked what would have happened if the storm had come across at a slightly different angle. A heading 10 degrees further south than the real one would have produced a wave about 6% larger. 20 degrees the other way, about 8% smaller. Push it out to a heading of 115 degrees, and the wave drops by a third. So the 1954 storm was not the worst case. It was near optimal. But the lake had more in it. Look at the shape of that. The deadliest wave in the recorded history of the Great Lakes was produced by a storm that was close to the right speed, on close to the right heading, And if it had been slightly closer to both, the water at Montrose Harbor would have been higher. None of which, so far, explains the thing that actually killed those people, because everything we've built up to here describes a wave leaving Chicago and traveling southeast toward Michigan. The pressure jump crossed the city first, the resonance happened out over the lake, the energy went away from the shore where the deaths occurred. So how did it come back? Here is the sequence, reconstructed, with the clock running on Chicago time. Around 7:20 in the morning, the squall line crosses the lakefront and goes out over the water, heading southeast at 65 miles an hour. Behind it, in the water, a long wave forms and begins to grow, because storm and wave are locked in step across a depth band that lets them stay locked. Around 8:15, that wave reaches the far side, the southeastern shore of Lake Michigan, the Indiana and southwest Michigan coast, Michigan City, and the dune country beyond it. Contemporary reports there put the water at 5 to 6.5 feet. There's damage. There's alarm. There are, as far as the record shows, no deaths, and I suspect that's partly luck and partly the fact that the storm had only just cleared that shoreline, so nobody had gone back out yet. Now, what happens to a wave when it runs into a coast? Some of its energy goes into the beach, into sediment, into heat, into the noise of water hitting things. Some of it runs up onto land and comes back, and the rest of it reflects. A coastline is a mirror for water waves. Not a perfect one, but a good one. And a long wave in the tsunami band is exceptionally good at bouncing, because it isn't the sort of wave that breaks and shatters. It arrives, it rises, it falls, and a large fraction of what came in goes straight back out. So by 8:30, the wave has turned around, and it is now crossing Lake Michigan in the opposite direction, toward Chicago. That alone would be enough to explain the timing. But it doesn't explain the size. And this is where the 2014 reanalysis found something that changed how I think about the entire hazard. Look at the shape of Lake Michigan's eastern shore on a map. It is not a straight line. It curves. It bows inward, concave, a long, gentle arc running from the Indiana state line up past Holland and Muskegon. A concave mirror does not just reflect, it focuses. The wave that arrived at the Michigan coast that morning had a front something like 93 miles wide. The curved shoreline reflected different parts of that front in slightly different directions. And those directions converged. By the time the reflected wave was back out in the middle of the lake, that 93-mile front had been squeezed down to about 31 miles. The same energy, a third of the width, and then the bottom got involved. As the narrowed front approached the Illinois shore and moved into shallower water, it refracted, the way light bends entering glass, turning the crest until it ran almost parallel to the shoreline, which is the worst possible orientation because it means the entire length of the crest arrives everywhere at once, instead of sweeping along the coast and spreading itself out. The researchers who worked this out described the mechanism in terms borrowed from the study of rogue waves in the open ocean, where the same geometric trick, energy from a wide front converging into a narrow one, is one of the accepted ways a freak wave gets built. So the water that came over the breakwater at Montrose Harbor at 9:30 in the morning had already crossed Lake Michigan twice. It had been generated by a storm that was, at that moment, 60 miles away over Michigan farmland. It had bounced off another state, and it arrived taller at Chicago than it had been when it left Chicago, because the far shore had aimed it. That's the answer to the hook. That's what the coroner's jury didn't have. There's a smaller correction inside the same paper that I want to mention because it shows how careful this work has to be. The Wilson Avenue crib gauge recorded a second disturbance a few minutes after the main one, with a period of about 15 minutes. Ewing's group and Plotzman both took it for a high-frequency component riding on the main wave, and it got a name, the second surge, and it stayed in the literature for decades. It wasn't a component of anything. It was the destructive wave itself, bouncing off the Chicago shoreline and heading back out to sea, caught by an instrument that happens to sit 2.5 miles offshore and therefore sees the outgoing echo almost immediately. It never touched the coast. It contributed nothing to the disaster. Platzman couldn't have found it because his grid squares were 2.5 miles across, and the feature was smaller than one square. 60 years of a phantom, produced by a gauge in an unusual place, and a model with a coarse mesh. That's the ordinary texture of this kind of work. And there's one more thing in the water that day, which explains the ugliest detail in the whole account: the 34 hours. Alongside the traveling wave, that same squall line generated a second family of waves entirely, called edge waves. These are waves that get trapped against a sloping shoreline. They can't escape into deep water, so they run along the coast, hugging it, sometimes for a very long time. They have their own resonance condition, worked out by a mathematician named Harold Greenspan in the 1950s, and it's satisfied when the alongshore component of the storm's motion matches the speed the edge wave wants to travel at. That morning, on Lake Michigan, both conditions were satisfied at once. The storm was moving at the right speed to pump a traveling long wave across the open lake, and at the right angle to pump edge waves along the eastern shoreline. The 2014 study noted that simultaneous generation of both wave types in a single basin hadn't been documented before. Those edge waves ran counterclockwise around the lake from the Michigan side, up and around, and started arriving at Chicago from about 10:15 in the morning onward, not as a dramatic surge, as a persistent 1.5 foot slop of currents and rising and falling water that would not stop. That is what the Chicago Daily News was describing when it reported that recovery crews were fighting strong currents and clouded water for a day and a half on a lake that looked, to anybody standing on Lakeshore Drive, completely calm. Now look hard at the shape of this, because everything that follows depends on it. The hazard is not the storm. The storm is the trigger. The hazard is a wave that outlives the storm, travels independently of it, can arrive from a direction the weather never came from, and reaches the shore at a time when every visible signal says the danger is over. The people who study this call it decoupling, and it is the single most dangerous property this phenomenon has. A hurricane announces itself. A tornado announces itself. This thing announces itself and then leaves, and the announcement and the arrival are separated by a gap long enough for a beach to refill. And there's something in this story I did not expect to find, and which I think is the most quietly remarkable fact in it. 10 days later, on July 6, 1954, it happened again. Same lake, same summer. A second event, and by some measures, a larger one. The recorded water level oscillation exceeded 4 feet in places, and the harbor master at Belmont Harbor told the Chicago Tribune that conditions on the lake were much more severe than they'd been on the 26th. Warnings went out. The beaches were cleared. Nobody died. 3 months before Ewing, Press and Dawn published the paper that founded this field. Somebody in Chicago, working with 10 days of very expensive experience and no theory at all, made the right call and emptied the shoreline. The city also went out and bolted cables and posts into the concrete of its breakwaters so that anyone caught out there would have something to hold. They called them siege fences. Wrong word. Right instinct. That is where adaptation to this hazard begins. With a harbor master, 11 years before the first forecasting chart existed. A reconstruction of a 1954 event, however careful, has a weakness that any honest reader should press on. The people doing it already knew the answer they were looking for. They knew a wave hit Chicago. They knew when. And they knew what killed people. A model built to reproduce a known outcome will usually manage to reproduce it. What the theory needed was a case where nobody knew the answer in advance. A different lake, a different depth, a different resonance speed, and a full set of modern instruments watching while it happened. It got one on May 27, 2012, on Lake Erie. Erie, remember, is the shallow one. Its central basin runs about 65 feet deep, which puts its long wave speed near 31 miles an hour. 65 is Lake Michigan. Erie is 31. If the mechanism is real, then Erie should be vulnerable to a completely different class of storm. Not derechos ripping across at freeway speeds, but ordinary summer thunderstorm complexes ambling southeast at the pace of highway traffic. That afternoon, 2 mesoscale convective systems came down out of Ontario and out over the lake. The Cleveland radar was watching. And this is the piece that makes the Erie case decisive, because Doppler radar doesn't just show you where rain is, it measures the speed of what's moving toward or away from the antenna. The analysts went into the radial velocity data and picked out 3 distinct outflow bands crossing the lake, each with its own speed. The first was traveling at about 31 miles an hour. That is the resonant speed for that basin, measured off an independent instrument with no water level data involved, matching a number computed from nothing but the depth of the lake and the strength of gravity. The second band was moving at about 42. The third arrived later that night, and at Burke Lakefront Airport on the Cleveland waterfront, the wind went from about 4 miles an hour to about 31 in under 2 minutes, with a barometric jump of a bit more than half a millibar. Now the water. 7 water level gauges along the Ohio and Pennsylvania shore recorded the day. The largest response was at Fairport Harbor, east of Cleveland, an oscillation of about 11 inches in amplitude. First arrivals showed up around 1:15 in the afternoon local time. Small, about 4 inches. Then, in the space of 23 minutes, the gauge recorded a rise of 5 or 6 inches followed by a drop of about a foot. Think about what that is at a shoreline. Not a wave you'd photograph. A foot of water leaving in 20 minutes across an entire coast. Then comes the check I find most satisfying in the whole literature. Cleveland's gauge and Fairport's gauge are about 25 miles apart along the shore. Cleveland recorded the same train of edge waves 45 minutes after Fairport did. 25 miles in 45 minutes is about 31 miles an hour, which is the edge wave speed the theory predicts for that shelf. 2 gauges, a stopwatch, and a prediction that had no room to wriggle. You could have done that calculation on the back of an envelope in 1960 if anyone had thought to look. And there's a negative result in the same dataset that I think is more persuasive than any of the positives. Toledo showed almost nothing. Toledo is the western end of Lake Erie. It is the place that gets flattened by Seychelles. It is where the lake bottom shows up on the evening news when the wind blows hard from the east. On the 27th of May, 2012, in the frequency band where Tsunamis live, Toledo barely registered. That is exactly the sort of thing a wrong theory doesn't produce. If somebody were simply relabeling every unusual water level event as a tsunami, the most water level unstable harbor on the Great Lakes would top every list. Instead, it drops out, because Siege vulnerability and tsunami vulnerability come from different geometry, and the Western Basin has the wrong geometry for one and the perfect geometry for the other. Here's what the day actually did to people. Around 1:30 in the afternoon, on the shore east of Cleveland, witnesses reported to the National Weather Service that 3 waves came in about 5 minutes apart, 3 to 6 feet. Those are eyewitness figures, and they should be read as such. Around 3:30, off Lakewood, the Coast Guard pulled 3 people out of the water after a boat capsized in what was reported as a 6-foot wave. And then, at about 6 in the evening, near Madison, Ohio, more than 4 hours after the storms had crossed the shoreline and left, the water pulled back. 3 swimmers went with it. The retreating water carried them over a breakwater and half a mile out into Lake Erie. They were picked up by recreational boaters who happened to be nearby. Nobody died on Lake Erie that day, and that outcome owed a good deal to who happened to be out on the water at the time. The mechanism, when it was worked out, was the Chicago mechanism with the map rotated. The waves reflected off the southern shore of Lake Erie, crossed to the northern shore, reflected again, and the north shore of Lake Erie is concave. Same focusing, same energy squeezed into a narrower front. Same arrival long after the sky had cleared, at a location the storm never passed over. 2 lakes, 2 depths, 2 resonant speeds differing by a factor of 2, 1 mechanism. Now, the reconstruction of that day involved a hydrodynamic model at about 330 feet of resolution, driven by an atmospheric model run at 2.5 miles, and it reproduced the event. That's the good news. The bad news was buried in the methods section, and it is the reason a large part of the rest of this story exists. NOAA already ran an operational forecast system for the Great Lakes at the time. It's what the marine forecasts were built on. And when the researchers checked, they found that 3 fast-moving storms had crossed Lake Erie inside the window, and the operational system had captured none of them. Not one. The reason was mundane and structural. The system fed itself wind fields by interpolating between hourly observations. A squall line crosses a piece of a lake in 10 minutes. Interpolate hourly, and it simply does not exist. The operational model saw a calm afternoon. 2 of the authors on that paper were not researchers. Greg Mann is a meteorologist at the Weather Service office in Detroit. Kirk Lombardi was at the office in Cleveland. These are the people who write the actual warnings, sitting as co-authors on a study whose conclusion was, in effect, that the tools they had been given could not see this coming. The conclusion they published was that forecasting this hazard requires spatial resolution of about 1 kilometer and temporal resolution measured in minutes. Keep that requirement in view, because we're about to find out what the Great Lakes Observing Network actually delivers, and the gap between those 2 numbers is the whole problem. But first, the case that shows why the size of the wave has almost nothing to do with how many people it kills. 4th of July, 2003. Southeastern Lake Michigan, the sand country below St. Joseph where the dunes run for miles, and the state parks fill up on a holiday weekend. It was a good beach day. Light wind, small waves, sun. At about 10 minutes to 10 in the morning, a bow-shaped convective storm came across, moving east at roughly 65 miles an hour. Upwind, at Madison, Wisconsin, the barometer had jumped about 2.5 millibars in 5 minutes. At Lansing, Michigan, 4.5 millibars in 10. Over the beach itself, the storm lasted under 15 minutes. Then it was gone, and the weather went straight back to what it had been. Sun, light wind, holiday. Between about 12:30 and 3:30 that afternoon, 7 people drowned along that stretch of shoreline. The details, as far as they can be stated respectfully. At Warren Dunes State Park, a 15-year-old boy got into trouble in the water, and 2 adults went in after him, and none of the 3 came back, while a 12-year-old who was also in the water survived. 4 more people drowned at other beaches along the Michigan shore that same afternoon. It's often written up as 7 deaths at Warren Dunes, which compresses it. It was 7 deaths along one coast in one afternoon. Every one of them happened between 2.5 and 5.5 hours after the storm had cleared. The National Weather Service office in Marquette wrote it up at the time as a rip current case study. That was a reasonable call and, as far as it went, an accurate one. People were caught in rip currents. That is what happened. The question that sat there for 16 years was where the rip currents came from, because the standard recipe wasn't present. Rip currents are normally built by sustained wave energy, waves breaking over a sandbar, piling water up in the trough behind it, and that trapped water finding a gap in the bar and blasting back out to sea. That takes surf. Real surf for a while. The measured significant wave height at the time of the drownings was about 18 inches. 18 inches is nothing. 18 inches is a lake you'd let a 9-year-old swim in. In 2019, Alejandro Linares and his colleagues went back at it with a coupled wave and circulation model built specifically for that coastline. 500,000 elements. Grid spacing down to about 6 feet in the nearshore. Lake bottom shape from about 1 million lidar points. So the sandbars were where the actual sandbars were. They tested 3 explanations and killed all 3. Explanation 1. The water overtopped coastal structures. The wave was too small, killed. Explanation 2. Eyewitnesses were right, and the waves really were over 3 feet. The instruments say 18 inches. Killed. And that's a case of measurement overruling testimony, which happens more often in this field than people are comfortable with. Explanation 3. Ordinary wind-driven rip currents. The standing explanation. The wave energy that afternoon was not sufficient to build the rips that were observed. Killed. What was left was the Meteo tsunami. The gauge at Ludington had recorded about 13 inches. Milwaukee, about 14. The model put the wave at Warren Dunes at around 14 or 15 inches, with a period near 95 minutes, and critically, with the water pulling down to about 8 inches below normal on the backside of it. 14 inches. That's the whole wave. That's the thing that emptied a beach of 7 people. A slow, quiet, sunny day rise and fall, about the height of a bowling pin. Here's how it kills, and it's the drawdown that does most of the work. When lake level drops 8 inches across an entire shoreline, all the water sitting in the trough behind every sandbar suddenly has somewhere to go, and the only exits are the gaps in the bars. So it drains, all of it, through those gaps seaward, fast. The model found channel rips running at speeds up to about 2 miles an hour and lasting more than half an hour at a stretch, plus focused rips, plus currents deflected by structures. And because a Meteo tsunami doesn't arrive once, because the lake keeps sloshing afterward, the whole thing reinitialized over and over through the afternoon. 2 miles an hour sounds slow. It's faster than most adults can swim, and it's much faster than most adults can swim while frightened, in clothes, or while trying to hold on to a child. So the size of the wave has almost nothing to do with how dangerous it is. A 14-inch Meteo tsunami killed 7 people on a sunny holiday. A 4-foot one, 10 days after Chicago in 1954, killed nobody, because somebody cleared the beaches. What matters is the current it generates and whether anyone is in the water when it arrives. The next number needs handling with tongs. It is the most misused figure in this entire subject, and I've watched it get inflated in 3 different directions. The same 2019 study looked at 15 years of Lake Michigan incident records and found that 16% of fatal, dangerous current incidents and 12% of reported rescues happened on days when a Meteo tsunami was observed somewhere in the lake. In raw terms, 15 event days, 10 deaths, 37 rescues, against a baseline of 94 current-related deaths and nearly 300 rescues at Lake Michigan beaches. That figure has been reported as 16% of Great Lakes drownings being caused by Meteo tsunamis. It is not that, and the gap is enormous. First, it's same-day co-occurrence, not attribution. Meteo tsunamis are made by convective storms. Convective storms also make wind, waves, and perfectly ordinary rip currents. Some fraction of that 16% is 2 consequences of one storm, not one causing the other. The author's own language is that the incidents occurred on the same day. Their contribution is a mechanism proof from one carefully modeled event, and that is a real and important thing to have proven, but it is not an attribution fraction. Second, and this is the number that puts the whole hazard in proportion, the Great Lakes Surf Rescue Project has counted roughly 1,460 drownings across the Great Lakes since 2010. 10 Meteo tsunami coincident deaths sit against that. well under 1%. Third, no agency actually attributes drownings to this cause. The Weather Service's incident database classifies by current type. The rescue project counts all drownings. Neither has a tsunami category. There is no official count, and anyone who quotes you, one has made it up somewhere along the chain. I'm laboring this because the honest version of the hazard is more interesting than the inflated one. Tsunamis are not what's killing people on the Great Lakes. What's killing people on the Great Lakes is overwhelmingly boating without flotation, falls from structures, cold water, and dangerous currents on ordinary windy days at ordinary beaches. Roughly 100 deaths a year, most years, and the worst year on record, 2018, ran to 117. The tsunami matters because it explains a specific and otherwise inexplicable failure mode. It explains the days when people died, and every forecast, every observation, every instinct said the water was safe. Those days are rare. They are also the days where warning has the most possible value, because on those days, nothing else is warning anybody. One last thing about the 2003 case, and it's the sort of thing I think you should know about a field before you trust its tables. That same event appears in a major 2016 compilation at a height of about 5 feet and located in Indiana. The 2019 study, by an overlapping set of authors, puts it at about 14 inches in Michigan. Factor of 4 on the height, wrong state. Meanwhile, a press release about the 2019 paper described the wave as less than 4 inches, which contradicts the paper it was announcing. None of that is scandal. It's what an emerging field looks like from inside. But it does mean that when somebody tells you a Great Lakes wave was a specific height, the only correct response is to ask which instrument, in what units, measuring what. Which raises the obvious question: how often does this actually happen? In 2016, a group led by Adam Bechla, with Chin Wu, David Kristovich, Eric Anderson, David Schwab, and Alexander Rabinovich, did the thing that the whole field had been building toward. They took the entire Great Lakes water level archive and ran the filter across all of it. 32 gauges. An average of 17 years of record apiece, 6-minute measurements, which is to say tens of millions of individual numbers. The procedure was the one we walked through. High-pass filter everything at 6 hours, which erases the seasons, the setup, the seiches, and their harmonics. Then hunt through what's left for individual waves with a period under 2 hours and a height over about a foot. Then, for each candidate, go to the weather record for that time and place, and ask whether there was an atmospheric disturbance to blame, defined as a pressure gradient above about 1/6 of a millibar per minute or a wind above 22 miles an hour. 87% of the candidates had one. A storm passing right there at the right time. The remaining 13% the authors handled honestly, rather than cleverly. Some are probably gauge errors. Some are almost certainly real tsunamis whose storms were somewhere else on the lake entirely, because a reflected wave doesn't have to have a storm above it. When your mechanism includes decoupling, you have to accept that some of your detections will have no local cause, and you cannot then use the absence of a local cause as proof of anything. Here is the number that came back: 106 per year. That is how many waves of potentially dangerous size, over about a foot, in the tsunami band generated by the atmosphere, occur on the Great Lakes in an average year. Not once a decade, not a handful. 2 a week on average, somewhere on those 5 lakes, all year, every year. The distribution matters as much as the total. Lake Michigan gets about 51 of them a year. Erie, about 27. Huron, 17. Superior, 6. Ontario, 5. And when you look at which individual gauges see the most, the pattern is so clean it's almost rude. Calumet Harbor, on the far southern end of Chicago's lakefront, sees about 29 a year. It's the busiest tsunami station on the Great Lakes by a wide margin. Buffalo, at the eastern end of Erie, about 17. Alpena on Lake Huron, about 14. Kewaunee and Ludington round out the top 5. Now notice where those are. The stations with the highest counts sit toward the southwest sides of the lakes, which is the wrong side. Storms in this part of North America move roughly west to east. The generation happens over the middle of a lake. If these waves simply went where the weather went, the east coasts would be the hot spots. They're not, because these waves bounce. The southwestern shores of the Great Lakes are the reflecting shores. They are where the energy comes home after crossing, turning around, and being aimed by whatever curve the far coast happens to have. Chicago is not unlucky. Chicago is standing at the focal point of a mirror 300 miles long. I find that an uncomfortable piece of geography, and it does more than explain a statistic. It means the highest risk shoreline is systematically the one where nobody watched the storm happen. On the east coast of Lake Michigan, at least the squall came over your head first. On the west coast, the wave arrives from an event that occurred somewhere you couldn't see. Then there's the return level analysis. And this is where the 1954 event stops being unique and becomes something more troubling. Pooling the network, a wave of about 2 3/4 feet is a once-a-year event somewhere on the Great Lakes. 4 1/4 feet is a once-in-10 years event. And the gauge oscillation recorded during the 1954 Chicago disaster, the roughly 3 feet that the instrument saw, works out to a recurrence interval of about 3 years. 3 years. The wave that killed 8 people and became the founding case of an entire scientific field was, in amplitude, a thing that happens somewhere on these lakes every 3 years or so. It was not a freak. It was a Tuesday that landed on a Saturday morning at a crowded pier in a city of 3 million people, after a storm that had cleared and given everybody permission to go back outside. That reframing is, to me, the most important single result in the whole climatology. What's rare about the disaster was never the wave. It was the coincidence. The storm types break down about 78% convective, meaning thunderstorm systems split fairly evenly between organized linear structures like squall lines and messier complexes. The rest are associated with the fronts of extratropical cyclones, the big synoptic weather systems that sweep the continent in the cooler months. And then there's the seasonality, which is the finding I'd point to if somebody asked me for one piece of evidence that this mechanism is understood rather than merely described. You'd expect Meteo-Tsunami season to track thunderstorm season. Thunderstorms peak in midsummer, July, and August. So Meteo-Tsunamis should peak in July and August. They don't. On Lake Michigan and Lake Huron, the seasonal center of mass sits in late May. Why late May? When there are fewer storms then than in July. Because on those lakes, the limiting ingredient isn't storms. It's storm speed. Michigan needs a disturbance moving at 65 miles an hour to resonate, and that's fast. Late spring and early summer storms move faster, driven by a stronger jet stream and sharper temperature contrasts across the continent. By midsummer, the atmosphere has gone sluggish. There are more thunderstorms, and they're mostly ambling. And an ambling storm over deep water does nothing at all. Now the test. If that reasoning is right, then a shallow lake, which resonates at a much lower speed, should have its season shifted the other way, toward the slow storms of late summer. Lake Erie's Meteo-Tsunami season is prolonged, running from late spring right through into late fall, with its center of mass in late August. The shallow lake likes the slow storms. The deep lakes like the fast ones. Lake Ontario, with its own geometry, peaks earliest of all in mid-April. Nobody designed that result. It falls out of the same square root of gravity times depth we started with, applied to a calendar instead of a map, and the calendar agrees. One more thing from that study, and then we have to confront what all this evidence is actually made of. The authors noted, almost in passing, that their gauge analysis turned up more events than exist in the entire reported historical literature on Great Lakes water anomalies, going back to 1882. More events in a filtered archive than in 130 years of people writing things down, which says less about the lakes than about noticing. Roughly 100 of these happen every year, and the overwhelming majority are noticed by nobody, because a foot of water arriving over 20 minutes on an empty stretch of Michigan shoreline in April registers with nobody at all. It becomes an event only when it happens to intersect a pier, a marina, a holiday weekend, or a beach. So the hazard has been there the whole time, at roughly its current rate, through every summer any of us has been alive, and every summer before that. Which raises a question that turns out to have an uncomfortable answer. If we can count them this precisely, why can't we see them coming? Everything we've established rests on one body of evidence, the water level record. The gauges are why we can tell a siege from a surge, from a tsunami. They're why the climatology exists. They are the instrument that made this hazard visible, so it's worth asking what they actually are. NOAA's National Water Level Observation Network runs to a bit over 200 continuously operating stations, and roughly a quarter of them are in the Great Lakes, which comes out to something around 50 gauges scattered across 5 lakes and the connecting waters. Most of them are the same basic device. An acoustic sensor looking down a vertical tube at the water surface, housed in a protective well, wired to a transmitter. They report every 6 minutes. That number, 6 minutes, is going to turn out to be the hinge of this entire section. So let's find out where it came from. It came from paper tape. Before 1966, the standard American water level gauge was afloat in a stilling well connected to a spring wound clock, drawing a continuous ink line on a moving paper chart, a merogram. Beautiful things, and in principle continuous, but nothing in the workflow around them preserved fine structure. Somebody read the chart, wrote down the highs and the lows and maybe hourly values, and the paper went into a box. In 1966, NOAA's predecessor agency started rolling out the analog-to-digital recorder, which replaced the pen with a mechanism that punched a hole in a paper tape. Punching a hole takes time and tape costs money, so somebody had to choose an interval. They chose 6 minutes, 1/10 of an hour, which is a perfectly sensible interval for the thing the network existed to measure: tides. The network was built to measure tides. A tide has a period of about 12.5 hours. Sampling at every 6 minutes gives you 125 points per cycle, which is luxurious. Those punch tape recorders stayed in service until 2003, and when the network went fully digital, the 6-minute interval came along because it was the standard, because the historical record was in it, and because nobody had a pressing reason to change it. So the sampling rate of the instrument that defines the Great Lakes tsunami record is a 1966 decision about how often to punch a hole in a strip of paper. Now, how bad is that? There's a rule in signal processing called the Nyquist limit, and it's ruthless. To resolve an oscillation, you need to sample it at least twice per cycle. Sample every 6 minutes, and the fastest thing you can even nominally see has a 12-minute period. Anything faster doesn't come out blurry. It comes out as something else, some spurious, slower wiggle that was never there, or as nothing. And the tsunami band starts at 2 minutes. It gets worse when you look at how a 6-minute value is constructed. It isn't an instantaneous reading. NOAA's own measurement specification describes it as the average of 181 1-second samples, centered on each 1/10 of an hour, with outliers rejected. So each number on the record is a 3-minute smear. And then there's a 3-minute gap, and then another 3-minute smear. Run a 10-minute wave through that, and you don't just lose timing. You lose height because you're averaging the crest with the water on either side of it. And there's a third layer, which is the one I find almost funny in a bleak way. The sensor sits in a protective well. Wells are used partly for physical shelter and partly on purpose. Kessing on per to damp out high-frequency wave energy, because when your job is measuring mean water level, the chop is noise, and you want it filtered before it reaches the sensor. Stack those three together, and here's where you land. The instrument that made this hazard visible was designed for a slow signal, sampled at an interval chosen for punched paper, and deliberately housed in a device engineered to suppress fast fluctuations. We are measuring a phenomenon with a tool built to ignore it, which means every number in that climatology is a floor. 106 a year is a lower bound. The heights are underestimates, systematically. And NOAA's own review of the problem says so plainly. The 6-minute gauges have been used to estimate arrival times and amplitudes in post-analysis, though limitations in observing the peak amplitudes likely exist due to the lack of higher frequency observation, and real-time operational application has not been demonstrated. There is a fix, and it exists, and it went somewhere else. After the Indian Ocean tsunami in December of 2004, NOAA upgraded its coastal water level network for high-rate collection, 1-minute sampling, transmitted fast, specifically so a tsunami signal could be picked out of a record while it was still happening. The initiative was completed in 2007. New stations went into Alaska, the Pacific Islands, the West Coast, and the Caribbean. You can see the logic. Those are the coastlines with subduction zones offshore. That is where seismic tsunamis come from, and that is where the money should have gone. The Great Lakes have no subduction zone, so the Great Lakes were not a priority, and today, when you query the network, essentially no open Great Lakes station returns 1-minute water level. The high-rate tsunami portal lists none at all. The lakes are still on 6 minutes. The instrument gap doesn't stop there. About 2/3 of those Great Lakes gauges also carry a barometer. It's a decent sensor with an accuracy around 0.5 millibar. It reports, like everything else, every 6 minutes, and each reading is a 2-minute average. The pressure jump from a squall line is typically under 5 millibars and arrives in a handful of minutes. So the entire forcing signature of a meteor tsunami occupies roughly one reporting interval, at a magnitude only a few times the sensor's own accuracy. You will often see that something happened, reconstructing the shape of the disturbance well enough to compute its speed, and heading, which is what resonance requires, is a different order of demand. Offshore, it's simpler to describe. There is nothing. The Deep Ocean Tsunami Detection Network, the pressure recorders sitting on the seafloor that watch a tsunami cross open water, has a few dozen stations worldwide. 2 of them are in the western North Atlantic. None are in the Great Lakes. NOAA's own assessment states it without softening. In the Great Lakes, there are no offshore pressure sensors and no meteor tsunami wave-detecting infrastructure. There are buoys, plenty of them. The federal buoys, plus a large fleet run by regional partners, sea grant programs, universities, and utilities. They're good instruments and they save lives. They measure wind, waves, air, and water temperature. They do not measure water level, and they do not measure bottom pressure. And most of them come out of the water for the winter, because ice destroys moorings. Which means the observing network thins out in exactly the season when Lake Erie's meteor tsunami activity is still running, and when a lakeshore flood does the most damage. Radar is the one thing that works, up to a point. There are Doppler radars ringing every one of these lakes. Their coverage in plan view is very good, and radar is how the storm speed gets measured after the fact, which is the measurement that matters most. But radar beams travel in straight lines while the Earth curves away underneath them, so the farther a beam gets from its antenna, the higher above the surface it is looking. Out over the middle of a lake, hundreds of miles from any of these radars, the lowest beam is thousands of feet up. The layer being sampled is not the layer where the outflow is pressing on the water. So put the whole observing system on one page. Water level measured at an interval chosen for punched tape through a well designed to filter out fast signals. Pressure measured to about 0.5 millibar, 6 times a minute apart, on 2/3 of the stations. Nothing offshore. buoys that measure the wrong quantity and get pulled for the winter, and radar looking over the top of the layer that does the work. That is the sensing base for a hazard that requires, by its own researchers' published estimate, resolution of about a kilometer in space and minutes in time. None of that means the work is hopeless. It means we're about to watch a group of people try to close a gap that wide. And the way they've gone about it is more inventive than I expected. And it starts with a wave nobody thought could happen here. Friday, April 13th, 2018. Ludington, Michigan, halfway up the eastern shore of Lake Michigan. At the point where the lake narrows to about 62 miles across, there was no thunderstorm. That's the first thing that makes this case matter. Because for the previous 6 decades, every documented Great Lakes tsunami had a convective trigger, a squall line, a bow echo, a thunderstorm complex, something with lightning in it. The mechanism had become mentally welded to the trigger, the same way tsunami had been welded to earthquake, and for the same bad reason. Those were the cases people had looked at. What crossed Lake Michigan that morning was an atmospheric inertia gravity wave. The atmosphere is a layered fluid. Warm air over cold, denser below lighter, and like any layered fluid, it can carry internal waves, oscillations that run along the boundaries between layers the way swell runs across the surface of the sea. Disturb it, and the disturbance doesn't just dissipate. It propagates as a train with a rhythm. Because the Earth is rotating, the rotation participates in the restoring force, which is where the inertia in the name comes from. You can't see them. There's often no weather attached at all. They're waves in the pressure field, and mostly they cross the country doing nothing anyone would notice. This one carried a pressure change of nearly 10 millibars over 12 minutes. For scale, the Chicago squall in 1954 managed 3 millibars over 4 minutes, and typical squall lines run under 5. This packet was carrying 3 times the amplitude, in a smooth, coherent, repeating train, and it was moving from west-southwest to east-northeast at about 60 miles an hour. The local long wave speed across that narrow reach of Lake Michigan is somewhere between 58 and 69 miles an hour. You know what happens next. 3 pressure waves crossed Ludington through the late morning and early afternoon. The water followed each one. The gauge at Ludington recorded fluctuations of up to about 1.5 feet, crest to trough, and that gauge sits inside the harbor, up a drowned river mouth, in a spot that damps a fast signal and delays it. The model put the wave at around 2.5 feet just outside the harbor entrance, and then in mid-afternoon, hours later, a 4th wave arrived, larger than the ones before it. There was no atmospheric disturbance anywhere near Ludington at that hour. That wave had gone across to the Wisconsin side, bounced, and come back. Decoupling, caught in the act, in a fully instrumented modern case. The whole lake rang. Holland, down the coast, saw the signal arrive by way of coastally trapped edge waves running along the shore at close to 60 miles an hour. Milwaukee picked it up in early afternoon. Calumet Harbor, at the bottom of the lake, recorded edge waves arriving from both shorelines at once, from the Michigan side and the Wisconsin side, converging on the corner of the lake where Chicago sits. At Ludington, the water went over the breakwalls and submerged them. It flooded into city streets. It damaged shoreline cottages and public boat docks, and interfered with water intake pumps. Photographs taken during it show a harbor with no obvious weather in the sky. Then, by one account of the timing, the water was back to normal about 9 minutes later. Nobody was hurt. Nobody died. And Eric Anderson, the NOAA scientist who led the analysis, was straightforward about why. It was April 13th. The Ludington breakwall on a July afternoon carries somewhere between 50 and 100 people. In April in Michigan, with ice still on parts of the lake, it was empty. That is the entire difference between a research paper and a disaster. And it came down to the calendar. Now, the forcing split on that event came out at roughly 93% pressure and 7% wind. Set that against the other two numbers we have. Chicago in 1954, about 60% pressure, 40% wind. Northern Lake Michigan across many events, wind doing the majority of the work in about 44% of cases. So the balance between the two forcings isn't a property of tsunamis. It's a property of each individual tsunami, and it ranges from almost entirely wind to almost entirely pressure. That should bother you a little, and it bothers me. A mechanism whose ingredients vary that freely is harder to pin down and easier to over-apply. What holds the whole thing together, and the reason I think the framework is sound rather than elastic, is that the invariant isn't the forcing. It's the resonance condition. Every single one of these cases, from a 1954 squall line to a 2018 invisible pressure train, had a disturbance traveling at the speed the water underneath it wanted to travel. That is the one thing that never varies, and it's the one thing that could have failed to hold and didn't. Here's the part of the 2018 case that changes the outlook, though, and it's good news in a story that hasn't had much of it. An inertia gravity wave is easier to forecast than a thunderstorm. Anderson said as much directly. Short-range weather models can pick up these atmospheric pressure waves, whereas predicting exactly where and when a thunderstorm will form remains one of the hardest problems in the science. A smooth, coherent wave train in the pressure field is the kind of thing a numerical model handles well. Because it's large, organized, and governed by equations the model already solves. And the reconstruction of the Ludington event didn't require exotic tools. The atmosphere was simulated with a configuration mimicking the high-resolution rapid refresh, which is an operational NOAA model that runs every hour of every day. The lake response was computed with the Lake Michigan and Huron Operational Forecast System, which is not a research code either. It's the operational hydrodynamic model, the thing that already produces routine forecast guidance for those two lakes. Existing operational atmospheric model, existing operational lake model. Chain them together, feed the first into the second at fine enough time resolution, and the wave appears. That is the closest thing to a roadmap this field has, and it emerged from a wave that nobody expected, on a day when the breakwall happened to be empty. The follow-up work went straight at the resolution problem. A team at Michigan Technological University working with NOAA and Argonne and Tsunamis pushed the grid from about 1,600 feet down to about 33 feet, fine enough to actually resolve water going over the top of a breakwater rather than inferring that it probably did. 33-foot grid cells over a lake 300 miles long is a spectacular amount of computing, and it's the sort of thing that only makes sense if somebody has decided the answer matters. Somebody has. The question is, what happens between the model finishing its run and a person on a pier deciding to go home? And that turns out to be where this whole story gets stuck. To understand why the Great Lakes still have no warning system for this, you have to go to the Atlantic for a minute, because that's where the institutional turning point happened. June 13th, 2013. A derecho crossed the mid-Atlantic states and went out over the ocean off the New Jersey coast around 11 in the morning. At about 3:30 that afternoon, at Barnegat Inlet, a spearfisher in the water noticed the ocean flowing out, not receding gently, flowing hard for a couple of minutes, dragging divers seaward across a breakwater that normally sits 3 or 4 feet underwater and was now briefly dry. Then it came back, roughly 6 feet from trough to crest into the south jetty, and 3 people standing on that jetty went into the water. The weather at the time was overcast with a light easterly breeze and a calm sea. Half an hour later at Falmouth Harbor on Cape Cod, the water pulled back and then flooded in, and the harbor surged for the better part of an hour. More than 30 tide gauges up and down the eastern seaboard registered it, with peaks running from about 1.5 inches up to 10 inches, and the oscillation was picked up as far away as Bermuda and Puerto Rico. The mechanism, once it was worked out, was familiar. The wave went east, reflected off the edge of the continental shelf where the seafloor drops away, and came back to the coast under a clear sky, hours after the storm. But here's the piece that changed policy. A deep ocean pressure recorder in the Hudson Canyon, one of the buoys that exists specifically to detect tsunamis crossing open water, registered the wave and triggered. The alarm went off. And at the time, the alert was not recognized as a meteotsunami. The data was there. The instrument worked, the threshold was crossed, the signal transmitted, and the interpretation was missing because nothing in the operational chain was set up to ask whether an unexplained tsunami band signal off New Jersey might have come from the sky. It was a scientist at the United States Geological Survey Office in Woods Hole who first publicly proposed the explanation. There's a bitter footnote to that. A few years earlier, the Weather Service had funded a project with a Croatian oceanographic institute, one of the few groups in the world with real operational experience of this hazard, specifically to build the procedures and protocols for issuing meteotsunami warnings in the United States. It was terminated after a year for budget reasons. Not long after that, 3 people were knocked off a jetty in New Jersey by a wave that a buoy had seen coming. To be fair to everyone involved, that is exactly how hazard programs get funded in every country I know of. Something happens, and then there's money. 2013 is the event that convinced the Weather Service to treat meteotsunamis as a specific, previously unaddressed hazard rather than a curiosity. And the protocol they built afterward works. On May 15, 2018, the same deep buoy caught a signal of about 1.5 inches. Coastal gauges saw up to 14 inches. This time the warning center recognized what it was looking at, called the forecast offices in Mount Holly, New York, and Boston. And those offices put out statements to alert people on the water and along the shore. That's a functioning system. Not a fast one, not a precise one, but real. Now take it to the Great Lakes and watch it fall apart, because the first link in that chain is a deep ocean pressure sensor, and the Great Lakes do not have one. The current position, in NOAA's own words, is that there are no operational capabilities allowing forecasters to accurately model a meteotsunami source and determine its propagation in real time, even if a positive detection is made, and that the goal of a near real-time detection and forecast algorithm remains aspirational. There's also a decision about language that I've gone back and forth on. The Weather Service has deliberately chosen to keep the word meteotsunami out of its public products. The reasoning is documented. Forecasters were reluctant to use it because the public associates tsunamis with catastrophic inundation from submarine earthquakes. And the concern was that a new or special product would spark confusion or panic. So operational products describe outcomes instead, in phrasing like sudden water level rise or rapid inundation. I understand that decision, and I think it's defensible, and I also think it has a cost that nobody has fully priced. A hazard with no name in the products is a hazard the public never learns the shape of. Nobody develops an instinct for a thing they've never been told exists. Every safety behavior we're going to talk about in a moment depends on somebody standing on a pier, recognizing a situation. You can't recognize a category you've never been given. Then there's the timing problem, which is structural rather than a matter of judgment. The Weather Service's lakeshore flood products, the watches and warnings and advisories, are long fused. A watch goes out 12 to 48 hours ahead. A warning covers the next 12 to 24. Those windows are built for a storm system arriving tomorrow, and a meteotsunami has a period of minutes. The special marine warning is short-fused, 2 hours or less, which is the right time scale. But its criteria are thunderstorm criteria: winds over 34 knots, hail, water spouts. There is no water level criterion in it at all. So the one short-fused product available cannot be issued for a wave arriving on a sunny afternoon, because by then, the weather that would justify it has left. The product Great Lakes offices actually use for this sort of thing is the Beach Hazard Statement, which was designed for dangerous currents and rough surf, and does the job partly. Listen to how a working forecaster describes it. This is Quetzal Levens at the Weather Service office in Duluth in July of 2025, talking about an event on Lake Superior. These events are difficult to message because of their displacement in timing from the convective system that initiates them, and because of a sparse data network for tracking water level fluctuations, so some events may go unobserved, especially at night. And, in her words, there is no specific headline to issue for these events, though depending on severity, they might fit under a lakeshore flood advisory or a special marine warning. Might fit under in 2025. The event she was describing, incidentally, is the best 3-in-1 teaching case in the whole record, and it closes the loop on everything we've been arguing. On June 21st, 2025, the gauge at Point Iroquois, Michigan, at the eastern end of Lake Superior, recorded, in sequence, on one morning, a meteo tsunami of about 19 inches between 8 and 10 in the morning, then a wind-driven drawdown of about 43 inches over the following hour and a half, then a seiche rebound of about 45 inches, which is the largest in that station's 30-year record, and which kept the lake oscillating for days afterward. All three explanations. All three real. All three on the same trace, in the same morning, at the same instrument. The only thing that separates them is the filter. The meteo tsunami is the fast one. The surge is the slow one. The seiche is the ringing afterward. Read the record raw, and it's one incomprehensible squiggle. Split it by period, and it's 3 different physical processes with 3 different causes, and one of them can kill somebody on a beach 2 hours after the sun comes out. Down in the Duluth Harbor Canal that day, a geological survey gauge measured currents running at about 8 feet per second. Nobody was hurt. So what is actually being built? More barometers, for one, which is unglamorous and probably the highest value thing on the list. Since 2018, the Great Lakes Lab has been working with private industry to install additional barometers around the lakes and to speed up how often the existing ones report. They're also working with the National Data Buoy Center on algorithms that would let the next generation of offshore buoys detect and report abnormal pressure changes on their own. And there's the buoy. In 2021, an experimental buoy of the type built to warn Pacific coastlines about earthquake tsunamis was deployed in the middle of Lake Michigan. The Great Lakes Lab took ownership of it in 2024. It is one instrument in one lake, and it is explicitly a research platform rather than a warning asset. It has already done something remarkable. In December of 2021, that buoy recorded the pressure wave from the eruption of Hunga Tonga in the South Pacific as the wave circled the planet, showing up as a signature in the water level of Lake Michigan. An underwater volcano on the other side of the world, detected in a freshwater lake in North America by an instrument put there to watch for waves made by thunderstorms. If you want proof that the atmosphere and the surface of a lake are coupled tightly enough for this whole mechanism to work, that's it. 2 more ideas are in the pipeline. And both of them are attempts to get around the fact that nobody is going to fund a network of pressure sensors on the bottom of Lake Michigan. The first is to stop trying to measure the pressure field and start inferring it. Vasily Titov at NOAA's Pacific Lab tried using a sequence of weather radar images as a stand-in for the pressure forcing, on the reasoning that heavier reflectivity broadly tracks the higher pressure regions inside a convective system, then scaling the whole field against the pressure record at a single tide gauge. He fed that into a model called MOST, which already serves as the operational tsunami forecast model at the National Warning Centers. The predicted arrival times for the significant waves lined up well with what was recorded. Radar you already have. A model you already run. Feed one into the other. It's an ugly, resourceful, engineer's answer to an instrumentation problem, and I like it a great deal more than waiting for a budget line. The second is high-frequency radar, which is a different instrument entirely, a shore-based system that reads surface currents out to some tens of miles offshore. During the 2013 East Coast event, high-frequency radars operated by Rutgers detected the wave 47 minutes before it reached the coast. 47 minutes is not much. 47 minutes is enough to clear a beach, so that's the state of adaptation. A mechanism understood, a climatology measured, several plausible detection routes, no operational system, and an admission on the record that a real-time algorithm is still aspirational, which leaves the question of what a person actually does right now with the system that exists. I have to be blunt about the answer, because the alternative is worse. There is no official National Weather Service action rule specific to Great Lakes meteotsunamis. No federal document tells somebody standing on a Michigan pier what to do if the water suddenly withdraws. The generic tsunami safety guidance that does exist, the one that lists a sudden rise or fall of the ocean as a natural warning sign, is written for seismic tsunamis. Its evacuation instructions are keyed to feeling an earthquake and to mapped tsunami hazard zones, and the Great Lakes have neither. Extending that rule to a lake would be me extrapolating, and this is not a subject where I'm willing to invent guidance and put an official-sounding voice behind it. What does exist is useful, and it comes from 3 places. I'm going to give you each one whole, with the source attached, because a partial safety rule is more dangerous than no rule at all. The one document I found that addresses this hazard directly is a fact sheet from the Illinois Coastal Management Program, produced by the University of Illinois. That's a state coastal program, not the Weather Service, and it should be weighted accordingly. It splits its guidance by who you are. For swimmers, avoid dangerous current areas and swim where lifeguards are present, because swimmers can be carried far from shore by rip currents. For people on shore, move inland and seek higher ground. Its specific warning is that fishing and storm watching become dangerous when water levels rise suddenly and wash over piers or shoreline, potentially sweeping people into the lake. For boaters, navigate to deeper water, because waves build and amplify once they move into the shallows, and sudden changes in water level can disorient people in small craft and capsize them. And it states the core hazard plainly, in language I'd want on a sign at every trailhead down to a Great Lakes beach. In the Great Lakes, there is often no warning, because the storm causing a meteotsunami may occur over a different part of the lake, or the effect may occur hours after a storm has passed, and that delay compounds the danger to beachgoers who have returned to the water. The second source is the Weather Service's own approved product language for the Great Lakes, which sits in the Directive Governing Lakeshore Hazard Services. These are the words the forecast offices are authorized to use, so this is as close to official as this subject gets. In a lakeshore flood warning, for your safety, stay off breakwaters, piers, rock outcroppings, and beaches. Waves are often larger than they appear and can easily wash you away. In a beach hazard statement, in the form used by the Grand Rapids office, strong currents can pull swimmers into deeper water, and high waves can sweep people off piers. Remain out of the water to avoid hazardous swimming conditions, and do not venture out on piers. Check with local authorities about beach closures. The offices also publish a 3-level swim risk scale, and I want to give you all 3 levels because the interesting one is the bottom of the scale. Low risk means large waves and dangerous currents are not expected. And the official wording of that lowest level continues, However, dangerous currents may exist at any time near piers, breakwalls, and river outlets. At the lowest risk level on the scale, the pier is still dangerous. Moderate risk means breaking waves and currents are expected. Stay away from dangerous areas like piers, breakwalls, and river outlets, and always have a flotation device with you in the water. High risk means life-threatening waves and currents are expected. Stay out of the water and stay away from dangerous areas like piers and breakwalls. The third source is the current guidance, and this is where I need you to pay real attention, because there are two different escape rules in circulation, and applying the wrong one in the wrong place will hurt you. Start with what the Weather Service office in Grand Rapids teaches about structural currents, which is the category that kills the most people on these lakes. Their briefing material is specific, so here it is in full. What to know: a pier, whether steel, concrete, or rock, focuses the current. Water pushed along the shore hits the structure and has nowhere to go, except out along it, and the pier at Grand Haven is 1/4 of a mile long. The current is often too strong to swim back in toward the beach, and swimming out of it sideways will likely send you back into the oncoming large waves. What to do? Don't put yourself in that situation. Do not swim within 100 yards of a pier, especially on the side the waves are coming from. Do not jump off a pier because you may be jumping directly into a structural current. If you are caught in the current alongside a pier, get the attention of the people on the pier. And if you are one of those people, throw a life ring or a flotation device if one is available. The Green Bay office adds one branch to that. If a ladder is available on the structure, try to swim to it. Michigan Sea Grant puts the same rule in the form of a distance. Stay at least 100 feet away from any structure. Be aware that a long-shore current running parallel to the beach can carry you toward one. And avoid jumping off or swimming near piers because the currents there are often dangerously strong. They add 2 more branches. For an outlet current, where a river or channel empties into the lake, what if you're avoid swimming in or near the outlet. For a channel current running between the beach and a sandbar, the best escape route is to swim toward the shore and not toward the sandbar. You'll have noticed those two distances don't agree. Grand Rapids says 100 yards from a pier. Michigan Sea Grant says 100 feet from any structure. They're different agencies writing for slightly different situations, and the sensible way to hold both is to take the larger one, because nobody has ever drowned from standing too far away from a break wall. Now the escape rule itself, and the reason I flagged it. The older advice, which most Americans over about 30 were taught, is to swim parallel to the shore to get out of a rip current. That advice is being replaced, and the Great Lakes Surf Rescue Project, which is the organization that tracks these deaths, is explicit that it supersedes it. The current guidance is called flip, float, and follow, and all 3 words carry a branch. Flip, turn over onto your back and float. Float. The purpose of floating is to keep your head above water, to calm yourself down out of the panic and fear of drowning, and to conserve your energy. Follow. Follow the safest path out of the water. Assess which way the current is moving, swim perpendicular to it to get out of it, and then swim to shore. The reasoning behind the order is the part worth internalizing. As long as you are floating, you are alive. As long as you are struggling against a current, you are drowning because you are spending the energy you need to survive on a fight you cannot win. Floating buys time for rescue to arrive. It also buys the 30 seconds of clear thinking you need to work out which way the water is actually going, which is very difficult to do while you are exhausted and frightened and swallowing water. And the reason the parallel to shore rule fails at a pier should be obvious once it's said, at a pier. Parallel to the shore is into the pier. The Weather Service office in Duluth adds 3 things that have nothing to do with tsunamis at all, and that account for more Great Lakes deaths than every mechanism we have discussed put together. First, about half of current-related incidents occur near piers and breakwalls. Their slogan is "Steer clear of the pier," and given the numbers, it's earned. Second, on life jackets. Don't just bring it, wear it. Their reasoning is practical rather than moralizing. Try putting on a life jacket while you are already in the water and in trouble, and you'll find out why. Accidents on the water happen far too fast to reach for a stowed jacket and get into it. Third, drowning is swift and silent. It does not look like it looks in films. There is usually no shouting and no splashing, which is why they push the idea of a designated water watcher, one adult whose only job for a set period is to watch the people in the water and nothing else. And one more, which is the specific killer of the Great Lakes in early summer. Know the water temperature before you get in. The air can be in the 80s in May, while the lake is still in the 40s. Sudden entry into cold water can incapacitate a strong swimmer almost immediately. None of that guidance is Meteo Tsunami guidance, and I want to be clear that I'm not presenting it as such. It's the guidance that exists for a shoreline where a Meteo Tsunami is one of several ways the water can turn on you, and where the behaviors that protect you from a 14-inch wave arriving on a sunny afternoon are, as it happens, exactly the same behaviors that protect you on an ordinary windy Tuesday. Stay off the pier, wear the jacket, float first. That's what 70 years of this science currently converts into, at the level of a person standing on a beach. It amounts to something real, and it is also considerably less than the science now knows. Now go back and read the record again. That's the reward for all of this. Once you have a mechanism and a signature and a rough rate of occurrence, you can go into 140 years of newspaper columns and coroner's findings and harbor logs, and you can start asking whether the thing that happened was the thing they wrote down. Start with the case that works cleanly, because there's tape. May 30th and 31st, 1998. A derecho ran 975 miles from southern Minnesota to north-central New York in 15 hours. It killed 6 people, injured more than 200, and did about $300 million of damage. Gusts between Madison and Milwaukee were clocked between 100 and 128 miles an hour. Its average forward speed across that whole run was 65 miles an hour. You already know what that number is. It's the long wave speed of Lake Michigan. Out at White Lake, on the Michigan shore, a tugboat named the Stephen M. Asher was overturned and sunk. The crew got to the bank. NOAA's own Storm Prediction Center case page describes what did it as a return surge from White Lake after the winds had subsided, and files the whole thing under siege. Then, in 2004, 2 researchers went into the water level records and found the fast oscillation. About 5.5 feet at Calumet Harbor in Chicago. About 5.5 feet at White Lake. That's the reattribution done properly. Not by reinterpreting a story. By finding a signal in the right period band at the right time on an instrument. Now the harder cases, and this is where I have to be careful with you, because the temptation here runs strongly in one direction, and it's the direction that makes for a better video. July 4th, 1929. Grand Haven, Michigan. A holiday, an enormous crowd on the beach, reportedly tens of thousands of people. A storm came through and passed. Afterward, by the newspaper account, waves came in, and the water retreated, and 10 people went with it. One of them was a 16-year-old girl named Mildred Fifield, swept from the pier. 10 deaths. It appears in the compiled dataset at roughly 20 feet, the largest figure in the entire Great Lakes record. And the source for it, the only source for it, is the Grand Haven Daily Tribune of July 5th, 1929. There is no gauge record, there is no model. There has never been a peer-reviewed reanalysis of that day. And if you understand anything by now about what shoreline observations do to wave heights, you will treat that 20-foot number as an impression, not a measurement. So what can honestly be said? The timing signature is right. The waves came after the storm had passed. That detail matters more than the height, because a reporter in 1929 had no theoretical reason to invent it, no framework that made an after-the-storm wave interesting, and every reason to write the simpler and more dramatic version in which the storm did it. He wrote the awkward version. Awkward details in old sources are the ones worth the most, and the retreating water is right too. That's the drawdown, and we now know from a fully modeled 21st century case that drawdown is where the killing currents live. 2 independent fingerprints in a source that had no motive to fake either. Here is what cannot honestly be said. We do not know what killed those 10 people. We have a physical process that produces exactly that pattern, at a rate of roughly 100 a year on these lakes, in a lake with the right depth, on the right kind of summer day. That is a strong candidate. It is not a finding. The same discipline applies right down the list, and the list is longer than you'd think. July 13, 1938, Holland, Michigan. Around 10 feet. The death toll is 3 in one archival citation and 5 in nearly every media account, and nobody has reconciled them. June 23, 1882, Cleveland. Around 10 feet. 1 person drowned. Barges were grounded, and the water reportedly put out fires at a steel mill, which is the sort of detail that makes me believe the account. Source: The Cleveland Plain Dealer. April 12, 1912, Ashtabula and Cleveland. A steamship broke her moorings and collided with a freighter. Source: The New York Times. May 31, 1942, near Cleveland. That's the one where 2 peer-reviewed papers disagree by a factor of 10 on the height and completely on whether anyone died. And then a few where the ground is firmer. May 5, 1952, on Lake Erie, was studied by William Don and published in 1959. About 3 feet at Buffalo, 6.5 at Madison, Ohio, 1.5 feet across the lake at Goderich, Ontario, with injuries at Madison. August 22, 1971, at Cleveland, was published by Murdy and Freeman. About 13 feet, 1 death. Rochester, New York, has 2 entries, from 1925 and 1979, 5 feet and 4 feet, recorded in an article whose title calls them seiches. Some cases fail the test outright, and it's worth saying which, because a mechanism that absorbs everything explains nothing. The Buffalo flooding of January 30, 2008, turns up online labeled as a meteor tsunami and appears in at least one state hazard planning document as a 16-foot seiche. It's a multi-hour wind event. It sits outside the 2-hour band, and it is not this. The 1844 Buffalo disaster, 78 dead, is wind, unambiguously. The record high water on Lake Ontario in 2017 and 2019 is seasonal hydrology playing out over months and belongs to a different subject entirely. There's one more that belongs in a category of its own. A Lake Superior event on July 13, 1995, appears in popular writing. Water falling and rising about 3 feet in 15 or 20 minutes, boats left hanging on their mooring lines, fluctuations from Rossport, Ontario, across to Marquette. It has no gauge citation, no paper, and no AA document, and it falls just outside the window the climatology examined, which starts in 1996, so it was never confirmed. It was also never refuted. It was never looked at. That's a different kind of unknown from an unexplained one, and I think the distinction is worth naming because these two get collapsed together constantly. An unexplained event has been examined and resisted explanation. An unexamined event has simply never had anyone's attention. Most of the mystery in most subjects is the second kind, and calling it the first kind is how a plain gap in the archive gets promoted into an enigma. So here's what the mechanism actually gives back to the historical record, and it's less than a diagnosis and much more than nothing. Before this work, those events had no home. They were freak waves and tidal waves, and those phrases are a shrug with a noun attached rather than an explanation. Something happened, it was strange, write it down and move on. And once an event has been named that way, nobody ever comes back to it, because the name closes the file. What exists now is a physical process that produces precisely that signature. A sudden rise on a calm shore from a storm that has already gone, followed by a drawdown that pulls hard, and then hours of unsettled water on a lake that looks fine. It has been measured, modeled, tested on 2 lakes with different depths, confirmed against radar and against the calendar, and it happens about 100 times a year. That means those old accounts are no longer strange. They're consistent. And an account that's consistent with a known process is an account you can reopen, which is not the same as an account you can close. 10 people at Grand Haven on a 4th of July in 1929, 3 or 5 at Holland in 38, 1 at Cleveland in 1882, and 1 in 71, and an unresolved number in 42, 8 at Chicago in 54, and 7 along the Michigan shore in 2003. For the last 2, we know. For the middle ones, we can argue from instruments. For the oldest, we have a mechanism that fits and no verdict. And the correct thing to do with that is say so and leave the file open. Go back to the breakwater one more time, and this time you get to know what they didn't. Montrose Harbor, Chicago, 20 past 7 on a Saturday morning in June. The squall comes over the lakefront, hard and brief. Wind to 56 miles an hour in the space of a minute. Rain. The barometer lifts 3 millibars in 4 minutes, which is a pressure change nobody standing there can feel, and which is at that moment pressing the surface of Lake Michigan down by about 1.25 inches across a front 90-odd miles wide. The storm crosses the shoreline and goes out over the water on a heading of 135 degrees southeast at 65 miles an hour. The water underneath it, in that depth, wants to travel between 60 and 67. That's the whole thing. That's the entire disaster, decided in the first 4 minutes, out where nobody is looking, by a coincidence between the speed of a thunderstorm and the depth of a lake. The storm is over Chicago for about half an hour. Then the wind falls to nothing, and the sky opens up and the lake goes flat. And every visible piece of evidence available to any human being on that shoreline says the danger has passed. They are not wrong about the storm. The storm has passed. While they walk back out onto the concrete, a long wave is crossing Lake Michigan, growing as it goes, being fed continuously by a disturbance moving at exactly its own speed. It's about 2 feet high out there, and it's 93 miles across. And it is completely invisible from a boat, let alone from a beach. At 8:15, it reaches Michigan. It floods a shoreline in Indiana and southwest Michigan and frightens people badly. Then it turns around because that's what long waves do at a coast, and the coast it bounces off is curved. So the 93-mile front comes back as a 31-mile front, aimed. At 9:30 in the morning, it arrives at a lakefront under a blue sky, and 8 people are lost. 2 hours and 10 minutes. That is the gap this whole subject lives in. The coroner's jury wrote down that it was a seiche caused by atmospheric conditions, otherwise an act of God. I've been hard on that phrase, and I want to take some of it back because they were half right in a way that deserves credit. It was caused by atmospheric conditions. They got the causal agent correct in 1954 with no theory whatsoever, working from nothing but the observation that a storm had gone through. What they lacked was the machinery in between, and the phrase at the end, otherwise an act of God, is what you write when the machinery is missing. There's no superstition in it. It's an honest declaration of the boundary of knowledge, like chested and as the filed in the language available at the time. What has changed since is us. The lake is doing exactly what it was doing then, roughly 100 times a year, on every one of the 5. What changed is that the sentence is no longer true. There's a mechanism where the blank space used to be, with a name, an equation, a measured rate, a season, a preferred shoreline, and a documented failure mode. That's what the last 70 years bought. Understanding, which arrives before safety does, and saves nobody on its own. The city's other response that summer was to bolt cables and posts into the concrete of its breakwaters so that a person caught out there would have something to hold on to. They called them sachet fences, using the wrong word for a thing they'd correctly identified as a place where people get swept away. Wrong word, right hardware. And in a story where the sophisticated end of the response is a 33-foot computational grid and an experimental buoy that once detected a volcano in the South Pacific, there is something clarifying about the fact that the oldest piece of adaptation on this shoreline is a handrail. The pattern is simple enough to carry around and it costs nothing. A storm crosses a great lake. It leaves. The sun comes out and the water goes flat, and everybody goes back down to the beach because that is the reasonable thing to do and always has been. That is the situation to watch for. The hour or two after the storm, on a shore that looks completely safe, particularly on the southwestern side of any of these lakes, where the far coast has been aiming things for 10,000 years. Now, one thing I'd like from you, and it's not a small thing because this is a subject where the archive is far thinner than the phenomenon. Around 100 of these happen every year, and almost none of them get written down anywhere. Not because they're hidden, because a foot of water arriving over 20 minutes on an empty stretch of shoreline is nobody's news. The people who see them are people who happen to be standing there. So if you've lived on one of these lakes, or spent summers on one, and you have ever watched the water do something the weather didn't account for, put it in the comments. A harbor that drained out and came back, boats sitting on their lines at a dock that went under on a calm afternoon, a beach that emptied and refilled while the sky stayed clear. Tell me the lake. Roughly where along the shore, and roughly when if you can. I'm asking because that is precisely the class of observation that never reaches an instrument, and reading a few hundred of them in one place is the closest thing to a survey this hazard has ever gotten from the people who actually live with it. And if you want more arguments like this one, taken apart carefully and put back together with the evidence showing, subscribe, and hit the like button on your way past. It helps this reach the people it's for. Let me finish on the instrument rather than the wave. The water level record. A strip of paper, or these days a column of numbers, one every 6 minutes, on a network built to measure tides, in a well engineered to filter out exactly the signal we've spent this whole time chasing. Everything in this story came out of that. The mechanism, the climatology, the seasons, the reflection, the correction to a paper from 1954, the reason 7 people drowned on a sunny 4th of July under a wave the height of a bowling pin. All of it was already sitting in an archive that nobody had filtered, which raises a question I'd rather leave standing than answer. What else is in there?